it is my pleasure to introduce our Dean, distinguished speaker, and also the chemistry seminar speaker for today, Professor Ajayan Vinu, who is a laureate professor and director of the Global Innovative Center for Advanced Nanomaterial at the University of Newcastle, Australia. He held the position of Global Innovation Chair, Professor, and Director of the center at the same university. From 2015 to 2017, he served as a full professor of nanomaterial at the Future Industry Institute, University of South Australia. Between 2011 and 2015, he was a full professor and also an ARC Future Fellow at the University of Queensland, Australia. Before his relocation to Australia, he worked as a senior researcher at the institute or at the National Institute of Material Science, Tsukuba in Japan. Following 2 years as we call it ICYS, I think this is International Center for Young Scientists in Germany. Over the past 2 decades, he has made a very significant contribution to the field of nanoporous materials and their application in sensing, energy storage, absorption, separation, and catalysis. His research achievement has been recognized with many international awards. I mean, if you look at the CV, maybe we need to spend 5 minutes to cover the award he received in the last 15, 20 years. And he has authored over 550 publications in high impact journals, which have received more than 39,000 citations, and resulting also in an H index of 101. It's a very, very impressive number for H index and also for citation. His pioneering work include advancement in mesoporous carbon nitride, boron carbonitride, biomolecule, and fluorines. Develop also innovative polymer chemistry and nano-templating techniques. Finally, according to the Stanford University in 2020 database, he has been ranking the first in Australia and also the 7th global, I think, worldwide among the top 2% of scientists in materials over the last 2 decades. So now we welcome Professor Vinu at KAUST, and the floor is yours.
Thank you. Thank you, Omar, for the kind introduction. He said, my name is Vinu, I'm coming from Australia. So today I'm going to talk about nanomaterials-based solution for clean energy and environment. And before going to the talk, I would like to give a brief introduction about where I'm coming from. So when I say Newcastle, I mean, many people think that it's a Newcastle in UK, which is quite famous, and Newcastle in America, and the Newcastle in Australia. So I'm from the Newcastle in Australia, and this is the place that the University of Newcastle is located. And we are ranked number 174 in the world. We have almost 37,000 students in 5 different campuses. The Global Innovative Center for Advanced Nanomaterials, I mean, you see here, we call it as C₃N₈, and it's located at the College of Engineering and Science and Environment. So the Newcastle is just located 2 hours away from Sydney. I think you all know about Sydney, right? So it's a very beautiful city with Opera House and Darling Harbour. And people who have not visited Newcastle may say that Sydney is the most beautiful place. But I think Omar visited Newcastle. And when you come to Newcastle, you will change your mind. It's a heaven on earth. Why I say it's a heaven on earth? It is surrounded by beautiful bays with the soft waves, with the whales and so on in one side, and other side is a mountain, very beautiful mountain with a lot of wild birds and small animals, and then you will hear that beautiful sound. And then the water is a bluish in color, and the other side is a desert. Can you imagine that a place with a lot of bays and mountain and desert in one place, right? In one side we are living there. People, after retirement, they come to Newcastle. But it's not only for the retirement, but also to do good science. And the University of Newcastle is the only university at the Newcastle, so we don't have any competitors. So I like to welcome you to come to Newcastle and enjoy the beauty of Newcastle, and also do collaboration with our center, which is a world-class center that I established in 2017 with a clear vision. Our vision is to be creative and diverse and responsible world leader in material science by developing a fundamental understanding and groundbreaking technologies and solution through IQ. So we call it as IQ because of the innovation and intelligence and interdisciplinary collaboration. That is the prime theme of our center, but that is in collaboration with academic and industry partners for solving the global issues. When I say solving the global issues, we use the nanomaterial based solution for solving them and helping the society. So there are key problems that we are taking to tackle it. The first one is the carbon capture and conversion, and that will save the world because it is causing this global warming. And we are also developing a clean energy solution using the nanomaterials based technologies, especially the hydrogen, batteries and supercapacitors and so on. And also we use the nanomaterial based solution as a drug delivery medium for cancer treatment. So that's what we say, that we use this nanomaterial based solution for solving these global issues and helping the society. So we have close to 70 people in our center. So it's a 50-50, it's the male and female from 12 different countries, and with advanced facilities. So I think in any universities that you go, you have a centralized facility, but the C₃N has got its own facility with a high resolution TEM and ACM, Raman, in situ Raman, high energy X-ray, and several photocatalytic reactors and so on. You name any facilities that you have in our center. And our center has been also actively collaborating with top academic and industry partners, and some of the industries are located in Saudi Arabia, Aramco and SABIC, and also the Middle East, the Abu Dhabi National Oil Company, and India, Carbonova, Apex Labs, and many mining industries in Australia. And they are the one who have been supporting our center, and they help us to do some kind of advanced research. And we have been also actively collaborating with the top universities around, in India and around the world, right? And that help us to do some cross-disciplinary research to solve the problems together that the world is facing. And I have been also the director of 2 international centers, Busan National University C₃N Joint Centers. It's a $6.5 million given by Korean government, and Yokohama National University and C₃N Research Initiative, that is 5 years program supported by MEXT, that is also several $1 million grant. So this is about my center. So in my center, there are 3 groups. So one of the group is run by me, and of course I'm also the heading the center. That's a nanoporous materials group. So we have around 40 plus people. So nanoporous materials, I'm quite interested in this one because of the fact that they can offer a highly ordered porous structures, very high surface area, large pore volume, and uniform pore size distribution. And these properties make them available for various applications. You take it for absorption, catalysis, energy storage, drug delivery, and so on. However, the efficiency of these materials in this application is mainly dictated by its structure, morphology, and functional element. So what we do in our center is to make a new family of advanced nanoporous materials with the highly ordered structures with the different chemical compositions like carbons, nitrides, fullerenes, biomolecules, amorphous and crystalline metallosilicates, and so on, with the highly ordered porous structures. And once we make the material and we try to control the morphology and the porous structures and even functionalities of the materials inside the porous channels to introduce new properties to this material. And once we have the materials and manipulate them with the different characteristics and we apply them for a different applications. So this is what we have been doing for the last 25 years or so. So the material fabrication and surface functionalization control, and we use the theoretical calculation to understand and predict the properties of the material, and then we apply them for various applications. There are several new materials that we have discovered, and some of them are shown here. The carbon nano cage and carbon nanocube. They have a three-dimensional cage type porous structure with a surface area in the range of 2,000 to 4,500 meters square per gram. And many people have been using this material for energy storage application. And we are the first one who introduced the nanoporosity in a highly ordered nanoporosity in a carbon nitride, boronated and boron carbonated material, even in the fullerene nanostructures with the C₃ and C₃. And several conducting polymers and semiconducting nanostructures, even the soft material and mesoporous superacidic material with a very, very high bronzed acidity, and we can use it for the cracking reaction. And all these materials are in the powder form, but we can make such materials in a film form as well. And some of them are shown here. It's a carbon films with the hierarchically ordered structures and even the biomolecule, nanoporous, cytochrome C, lysozyme, and so on. So these are all the fascinating material, from the hard material to the soft material, even to the living molecule. So we can introduce the highly ordered nanoporosity with a very high surface area. The question is, can we use this material for solving the global issues? So one of the global issues that I'm talking about is the CO2 emission to the atmosphere. 400,000 years ago, the CO2 level in the atmosphere is less than 300 ppm. It was going up and down till 1950, as you can see here. After 1950, the CO2 level increased quite significantly. Now it's 430 ppm. You know, the reason for the huge rise in the CO2, this is mainly coming from the fossil fuel, right? And now the population is 8 billion people. Everybody needs energy, and they consume 580 exajoules of energy. 1 exajoule is 1 billion tons of joule, right? And in 2021 alone, we liberated 36.5 billion tons of CO2 to the atmosphere. Why CO2 is a big issue? It's a small molecule. I think Ettore has been working a lot on this one. I mean, capture of the CO2 and then using his MOF material, and made a revolutionary research on it. I mean, many top researchers in the world have been working very actively to get rid of this one. You know why? It's a small but nasty molecule. Plants love them, we hate them, because it has the tendency to absorb heat, right? When it's in the atmosphere, it absorbs heat, and the heat will be reflecting back to the earth and warming up the earth. And you may be asking me why we didn't have the global warming, you know, till 1950 or till 2000 or whatever. Because nature has its own mechanism. Because, you know, we have an ocean, then ocean can capture the CO2 molecule, but it can capture the 70 to 80% of the CO2. But if the CO2 level is so high, the ocean gets acidified. and it may affect the living organisms in the ocean. Do you think the problem will stop here? No. Because now the population is 8 billion. In 2030, the population will be 8.5 billion. 2050, maybe 9.7 billion. And 2100, maybe 11.2 or 11.5 billion. Everybody needs energy. In 2050, you need 750 exajoules of energy, right? And that may liberate maybe 40 billion tons of CO2. And that's a huge problem. That's why many countries in the world, including the Kingdom of Saudi Arabia, spending billions of dollars to design and develop a new form of energy that won't emit CO2. And they have several strategies, like to increase the energy efficiency, to use the renewable energy sources like solar cells, and then carbon capture and conversion technologies, and find the energy source that won't emit any CO2, right? Or even public awareness or policy regulation. So it's like, you tell your kids or tell your friends to use the energy quite efficiently. So one of the key area that government is looking at is hydrogen-based technology. Why hydrogen-based technology? Because we may have a gasoline for another 50 years and coal for another 100 years. What will we do to get that energy for 8.5 billion or 9 billion people? We have to find another source, but find a source that shouldn't emit any CO2. And hydrogen is the key molecule. I mean, when you burn, there is no CO2 emission. It has got a high energy density, and it can be stored without losing its energy, large availability of resources, and we have economic potential. And currently, the hydrogen is mainly produced from the natural gases, crude oil, coal, and electrolysis. But it's the natural gas, crude oil, and coal. When you wanted to produce 1 kg of hydrogen, they produce almost 10 kg of CO2. And you can't use the current technology, right? When our demand will be 94 billion tons now, with a market potential of $185 billion. And 2050, the demand will be $530 million. The market potential, revenue potential is $3.18 trillion. But you can calculate, if you use the current technology, how much million tons of CO2 it will be liberated. Because with the current technology, you see here, the efficiency is very low. Of course, the cost is less, but it emits a lot of CO2. So therefore, people are jumping into green hydrogen production, electrolysis and photocatalysis. In the electrolysis, you need pure water. The cost is also very, very high, right? $7 to $8 per kg, right? On the other hand, photocatalytic approach, so the solar to hydrogen conversion efficiency with the current technology is a 1% efficiency. The cost is very high. But to reach the cost target is a 1.6 to 3.5, you need to have 5 to 10% of the solar to hydrogen conversion efficiency. But this may be an excellent technique because of the fact that we have large amount of the sunlight available, 885 million terawatt hour energy, right? But there is a catch. Everybody is talking about the energy available in the sun, right? But when you talk about the water splitting, but nobody was talking about where you will get the water, right? But even electrolysis or a photocatalysis, that's a huge, huge issue. So in the world, we have 330 million cubic miles of water. In that, 97% is a seawater, only 0.3% is in the form of surface water, I mean like lake water, river water, and so on. To produce 1 kg of hydrogen, you need 9 kg of water. But if you use the electricity, you need 55 kilowatt hour energy for producing just 1 kg of hydrogen. So just assume that you are converting the seawater into energy. So then you need to convert seawater into normal water and normal water into energy. To convert that, you need a 7 kilowatt hour just to convert 1,000 liters, right? And to split 1,000 liters of water, you need 5,500 kilowatt hour energy. You can simply calculate how much amount of energy that you need if you use the electrolysis, and how much amount of water that you need if you wanted to convert that 530 million tons of the hydrogen. But even now, people are fighting for the water. If you use this river water or a lake water, you are going to create another social problem. So the solution may be convert that seawater into hydrogen by using visible sunlight. And this is what, ladies and gentlemen, our center has been working on it. So can we use the advanced material-based technology to split seawater with the visible light with the highest solar to hydrogen conversion efficiency? But once you produce hydrogen, where you will store the hydrogen? That is another problem. So you have to integrate that one with hydrogen conversion technology, and then hydrogen to energy, and then energy storage technology, so that when the sun is there, you can convert seawater into hydrogen with the nanomaterial, and then the hydrogen can be used as a fuel to fuel cell, and that generates energy. That energy can be stored in the batteries and supercapacitors. When the sun is not there, and whatever energy stored here, if you wanted to use the electrocatalytic water splitting and to split water. And also the same material can be used for capturing the CO2 and convert that into methanol, and methanol can be used as a fuel for the fuel cell, and that generate energy. So the simple ultimate clean energy storage conversion device, you don't need any gasoline, you just need water and electricity and material. And with this, you can drive a car and without just emitting any CO2. So what you need is the integration of all this technology: water splitting, fuel cell, batteries, and solar cell, but this material, right? And that should have the potential to split the water. So this is what I'm going to present to you, how to make this fascinating nanostructures and how we can apply them for making this ultimate clean energy storage and conversion device. So in the next 30 minutes or so, I'm going to show you how to fabricate a series of material for water splitting, energy storage, carbon capture, and fuel cells, right? And then I will demonstrate you how these materials can be used for seawater splitting, carbon capture, and the energy storage and conversion technology. So first, the material. So the material I'm going to talk about is a graphitic carbon nitride, which is a fascinating material. It's composed of carbon and nitrogen. There are 5 different kinds of carbon nitride: alpha, beta, cubic, pseudo-cubic, and then graphitic carbon nitride. Among this carbon nitride, graphitic carbon nitride can be synthesized by chemical or molecular precursors at a low temperature and low pressure. But alpha, beta, cubic, and pseudo-cubic carbon nitride, which is quite stable material, you need extremely high temperature and pressure. And also you can't make in a large quantity. So therefore, many people have been working on graphitic carbon nitride. So not only for this synthesis, easy synthesis approach, but also it has got a unique molecular structures with the triazine and with the free NH2 groups on the surface, and it is a metal-free organic semiconductor with a band cap of 2.7 electron volt. And since it has got a basic NH2 group, and it can be also used as a basic adsorbent for capturing the CO2. So how to make this material? This material can be fabricated by just burning out high nitrogen containing organic molecule under Indian atmosphere, and you will get the graphitic carbon nitride, but with a less surface area. Even with the less surface area, people have been using this one as an adsorbent, electrocatalytic catalyst, or the photocatalyst. But unfortunately, the performance of the materials in the photocatalysis is very low because of the fast electron hole recombination and limited visible light harvesting because of the poor band cap, that is a 2.7. And what we have been doing in our center is to change that scenario. So we adopted a different strategy. So to increase the specific surface area, we have introduced the ordered mesoporosity in the carbon nitride material. So thereby, you have a material with a very high surface area and large pore volume. And that can increase the number of the active sites in this organic semiconductor. The second strategy is introduce the surface functionalities by replace some of the nitrogen atom with the carbon, sulfur, phosphorus or boron, so that you can tune the electronic properties of this material. And third one is just hybridized with other two-dimensional conducting nanostructures so that you can manipulate the electronic characteristics of the material. And most of the materials are in amorphous nature, but you can change the electronic property of the material by converting it amorphous into crystalline nano structures, right? And most importantly, change the chemical composition. Ladies and gentlemen, I wanted to tell you, so far, people have predicted the carbon nitrate has the stoichiometry ratio of C₃N₄. But my group has informed the scientific community that we can make a new family of the carbon nitrate material with the different carbon and nitrogen ratios, like a C₃N₅, C₃N₈, C₃N₁, and C₃N₇. And thousands of researchers around the world are now following this research because it was not theoretically predicted, but now they have confirmed that we can have the carbon nitrate material with a very high nitrogen content with a very high stability. So I'm going to show you first how to create the nanoporosity in the carbon nitrate material. So this was first introduced by me in 2004. We filed a patent, published in 2005 in Advanced Material. So what we have done is that we use the nano-templating strategy. So the nano-templating strategy is nothing but you take the template with a highly ordered nanoporosity and fill the pores with the necessary precursors, cross-link them, remove the template, and you will get the structure of the template in your material. This is similar like, the way you make brick or a tiles. So to make a brick, what do? You take the wooden template and put the clay on the template, the porous structure, heat it up to connect the bond, and remove the template, and you will get the structure of the template in your material. And you imagine to bring down the size 100,000 times smaller, right? And make this nanoporous silica template with the three-dimensional porous structures, and the pores are in the range of 2 to 10 nanometer. And fill them with the molecules, carbon and nitrogen molecule, cross-link them at a lower temperature, otherwise it will be exploded. And once it is polymerized, and you burn out all the hydrogen and so on to get the carbon nitrate material. So in this case, we use the carbon tetracovalent ethylene diamine. At a 90 degrees centigrade, it undergoes polymerization and carbonizes at 600 degrees centigrade, and you will get a highly ordered carbon nitrate with the linear arrays of mesopores, right? And this is electron anelular spectroscopy. The nitrogen content of the material is very low. It is a C₄N and it's not C₃N₄. It's got a pyridinic structure. But C₃N₄ has a triation structure. So since it has got a pyridinic structure with a very good conjugation, use a black color and is highly conducting. We call it as a conducting carbon nitrate material. To have a carbon nitrate with the C₃N₄ stoichiometry with the well-ordered porous structures, what we have done is we integrated the templating strategy with the diamino triazine molecule. So this undergoes polymerization inside the nanochannels at high temperature, and after removing the silica template by sodium hydroxide, you will get a highly ordered carbon nitrate. This is a lower angle excited diffraction pattern. You can see there's a sharp peak, and that indicates that it has got ordered porous structures, and the surface area of the material is 225 meters square per gram. You see the high surface area is coming from the well-ordered porous structures. And this is C₃N₄, and it's a yellow color, right? And what about its chemical structure? So we compare the chemical structure of the material with the bulk carbon nitrate with C₃N₄. It's almost similar. So that means that the prepared carbon nitrate with the nanoporous structures with the C₃N₄ stoichiometry has this triazine structure. So what about its performance? The visible light photocatalytic performance. And this is a bulk carbon nitrate, and this is our nanoporous carbon nitride with the C₃N₄ stoichiometry. So there is a huge increase in the hydrogen production. But is that enough for the commercialization? No, it's not even 0.1% of solar to hydrogen conversion efficiency if you really want it. And also it's normal water. So this may be mainly due to the fact that the band gap of the material is 2.7 electron volt and there is a fast electron hole recombination. So to overcome these difficulties, what we have done is to change the band gap of this carbon nitride material. And how we have done is, instead of diaminotriazine, we used diaminotriazole. So that has got a 2 carbon atom and 4 nitrogen atom. And again, we integrated this one with the mesoporous SPA15 template with the well-ordered porous structures. And they reduced the temperature a little bit from 550 to 500 degrees centigrade and remove the silica template by HF or sodium hydroxide, and you could get carbon nitride with the C₃N₅, and this was calculated with the CHN analysis. And you see here from the TEM images, it has got a highly ordered porous structures. And from the electron energy loss spectroscopy, one can clearly see there is a huge increase in the intensity of the NK cell excitation edges. And from the shape of the CK and NK shell excitation edges, you can see that there is a strong bonding between the carbon and nitrogen, and they are sp2 hybridized. But the wall structures are amorphous in nature. So interestingly, when we analyze the nature and coordination of the carbon and nitrogen in the carbon nitride with the C₃N₅, we found that there is a huge quantity of the sp2 hybridized carbon, which is completely different from the C₃N₄. And also there is a strong pi-pi stacking. That means it's a layered material. And C₃N₄ has a trisys triacin structure. C₃N₅ cannot have this trisys triacin structure, right? Because there is no sp2 hybridized carbon, and that is mainly coming from the triazole moiety that is here. So you have a combination of the triazole and triazine into this one, and that enhances the band gap of this material from 2.7 to 2.2 electron volt. So the visible light absorption capacity of this material is much, much better than the C₃N₄. So, and this is the world first carbon nitride material with the C₃N₅ stoichiometry with the highly ordered mesoporous structure, right? And we haven't stopped there. Can we make C₃N₆? Can we make C₃N₁ or N�8, right? So for C₃N₆, you have to have a completely different chemistry. So what we have done here is that instead of using the cyclic C₃ precursor, we use the non-cycling C₃ precursors, that is the aminoguanidine. So the aminoguanidine undergoes self-condensation to get diaminotetrasin, and this undergoes polymerization to get the stable tetrasin-based polymer in the highly ordered nanoporous silica template. And when we remove the silica template, and you could get carbon nitride with the C₃N₆, and that was again calculated by the CHN analysis. And these materials also having highly ordered porous structures. From the electron energy loss spectroscopy, you see here the intensity of the NK shell excitation is very, very high. Interestingly, we made 3 material using the template prepared at a different temperature, 100, 130, and 150. That means the template material with a different pore diameter, right? And when we use the different pore diameter, this template with the different pore diameter as a template, you see, surprisingly, we got carbon nitride material with a different band gap. And this is mainly due to the fact that when you have a material with a different pore diameter, it significantly controls the wall thickness of the carbon nitride after the preparation. And that changes the defect size or the electronic composition of those material in this wall structure. And see, because when you have a small pore diameter, and then the decomposition of this material is quite high. But in the case of the large pore diameter, with the molecular weight of the polymer that is formed is quite big, and it is very difficult to decompose. As a result, you get the material with a high nitrogen content, and then that also changes the band gap of this material. And this is not the only way. So you can change the carbon nitride material by changing the chemistry. But can we do it without, changing the chemistry and make the material with a different carbon to nitrogen ratio? So in this case, what we have done is we use the tetrazole as a precursor. That's a cyclic molecule with a 5 nitrogen content and 1 carbon atom, right? And it easily undergoes decomposition to get the cyanamide and then hydroxoic acid. That undergoes, polymerization at a different temperature. You can get carbon nitrate with the C₃N₅, N6 and N7. So you can make a bulk carbon nitrate, that means carbon nitrate with the no porosity, but also mesoporous carbon nitrate when you integrate that one with the template. So see here, when we use the temperature of less than 200 degrees centigrade, you get the C₃N₈, but it is quite unstable material. But C₃N₈ can be prepared at 300 degrees centigrade, and 400 and 450, you have carbon nitrate material with the C₃N₅ and C₃N₄. Interestingly, when you look at this XR spectroscopy and FTIR, you see the intensity of the NN bond that increases, that is coming from the triazole, that molecule, right? So that's why you have a different molecular structures, but now this is theoretically predicted, and it is not just a simple molecule, but it's the real material that you confirmed with the transition electron microscopy. And we use that one for the oxygen reduction reaction. When you have a material with a high nitrogen content, the current density that you are getting is much, much higher than the carbon nitrate material with the less nitrogen content, right? So what about is the stability of the material? So whenever you talk about carbon nitrate with the high nitrogen content, they may say that, oh, it will explode. So ladies and gentlemen, I just wanted to tell you, so we prepared this material at the temperature of 400 to 550 degrees centigrade. And it is highly stable at a room temperature. And we also checked that thermal stability of the material with the density functional theory calculation. You see, the phonon density of the state is quite positive. And also the formation energy of the carbon nitrate with the C₃N₄ is almost similar to that of the C₃N₅. So it is a quite stable material. What about the charge density profile? See, the C1 and C4 carbon atom has the most positive potential, right? So that means you have an uneven distribution of the energy on the surface of this material. Can we use that? It's a kind of wave-like surface on this material, but of course it's a flat structure you are seeing like here, but it is not that. You have this kind of, but can we use that one to the uneven distribution of the energy density to make another hybrid structure? So we have done that one, by integrating with the mesoporous, templating strategy. First, we made a graphene nanosheets, and then we put it in the mesoporous silica template, and then with the tetrazole. And once you remove the template, you get that graphene C₃N₅ mesoporous nanostructures. And when you introduce the graphene, the conductivity of the material significantly enhances, and that changes the performance of the material in oxygen reduction reaction. See the current increase from 5 milliampere centimeter square to 11.1 milliampere per second. This is one of the device in the ultimate clean energy storage and conversion device. So what about the seawater splitting data? See, and it increased from 300 to almost 800. This is a carbon nitrate with a C₃N₅ stoichiometry. The high performance is mainly due to the fact that so you have less the electron hole recombination, and it's a huge absorption of the visible light. But still, it is not enough, right? Because it increased from only 300 to only 800 after 3 hours of the reaction under the visible light photocatalysis. So can we increase the performance of this material, right? So now the band cap is 2.2, when increase from, degrees from 2.7 to 2.2. But what would happen if you change the surface composition of the material with a different heteroatom? So we use some kind of supramolecular assembly approach using the thiourea and trimesic acid, and we try to add sulfur and carbon into the carbon nitrate material with the C₃N₅ stoichiometry. This was just published in Advanced Energy Material. Interestingly, the conductivity of the material increases, and when we dope the carbon and then the sulfur, that one, and also that changes the band structure of the material quite significantly. So this is a photoluminescent spectra, and when you dope with the carbon and sulfur in the C₃N₅, there is a significant suppression in the electron hole recombination, right? And also significant rises in the photocurrent, and the conductivity of the material increases. As a result, so the performance increased from 300 to almost 7,500 micromole of hydrogen per gram. It's a significant improvement in the performance of this material. So I have shown you how to make the carbon nitride material with a different composition and with the highly ordered porous structures and with the different doping. But all the material that I have shown you are amorphous in characteristics. So what would happen if we change the amorphous wall structure into crystalline wall structure, right? And is it easy to do that? So to introduce the crystallinity in the carbon nitride material with the C₃N₅ stoichiometry or C₃N₈ or N₃, we added the alkali metal salts and adjust the temperature and change the precursors. So when you add the alkali metal salts or the potassium chloride or lithium chloride, it improves the polymerization and inhibit the decomposition of the precursors and destabilize the structures. As a result, you get the highly crystalline carbon nitride material, right? With a crystalline carbon nitrogen wall structure, right? So, and we also integrated that one with a supramolecular assembly. So in this case, we use the cyanuric acid and the triazole, right, with a different ratio. When we change that one, together with the salt assisted strategy, the morphology of the material changes from sheet shape to stake layer to triangular prisms. And that makes a huge difference in the final performance of the material. See, the materials with the different morphology, the sheet-like structures gives the performance of 12,000 micromole of hydrogen, and that is mainly due to the fact that it has got a much better the charge transfer than the materials with the rod-shaped morphology, right? And then we also made carbon nitride with the normal templating strategy and the non-templating strategy with the crystalline carbon nitride framework by using potassium chloride or potassium iodide as a salt. To make a mesoporous crystalline carbon nitride, we use the thiourea and silica nanoparticle, and we could get mesoporous crystalline carbon nitride after the calcination and the silica removing, as you see here, right? So band structures didn't change much. It's almost similar to that of the bulk carbon nitride. It's the range of 2.35 to 2 electron volt. And what about its performance? So the performance with an amorphous material, it was 12,000 after 5 hours, and when we use this 10% triethanolamine. But crystalline carbon nitride with the normal water, it's almost 20,000 micromole of hydrogen. And this high performance is mainly due to the fact that it has got the crystalline structures. And we also changed the triethanolamine to ethanol or methanol as a sacrificial agent, and it gives almost similar results. Interestingly, the co-catalyst amount we reduced from 3 weight percentage to 1 weight percentage, and we get the almost similar results. So these are all fascinating results, right? But to commercialize it, you have to think about the amount of water, right, and the cost of this the material, right, and also the performance, right? Now I'm going to show you. So I was talking about the splitting of the seawater into hydrogen. So we use the sulfur-doped mesoporous C₃N₅, but the bulk carbon nitride, it's a kind of serendipity results. We wanted to change the electrolyte, right? And we added some kind of sodium hydroxide into the solution or whatever. Surprisingly, what we found was quite fascinating. The performance increased from 300 to almost 30,000 micromole when we added the alkali metal salt into the synthesis, the reaction mixture. See, so normal water, it's a 2740, and with the seawater, it is a 6370. That means after 5 hours, it is 27,300. This is bulk carbon nitride with a surface area less than 10 meters square per gram. And when we use mesoporous carbon nitride with a sulfur doped system with the C₃N₆ with a crystalline framework, the performance increased to almost 50,000 micromole. And this is a champion data in the world, and this is the visible light for the carbon nitride. This is a visible light seawater splitting. And we tested the material with the water collected from different beaches. So it's a groundbreaking discovery, and this was the dream of every researchers in the world, to convert that seawater into hydrogen under visible light. So we have achieved in our center. So we collected the water from Caves Beach, Red Hat Beach, I think, Omar, I think you went to Nelson Bay and so on, and we collected water from there also. And it works very well. And with the Decusa photocatalyst, and this is a commercially available one, the performance is 2,500. But our material is almost 52,000 micromole, right? And just seeing, believing, and the solar to hydrogen conversion efficiency is almost 3, right? So when you look at this, see, there is no electrical connection, just visible light. We just shine it on our material at the seawater.
Oh yeah.
See here? How the hydrogen gas is coming out from the material, right? Without applying any electricity, just with the visible light, right? And the rate in which the hydrogen is produced, it is absolutely fascinating. And it is quite stable, and we have run it for several days and several weeks, and it was quite stable. And if you wanted to recycle it, and then you had to flush the salt with just normal water and then reuse it again, and then you can produce the hydrogen continuously. I mean, we haven't stopped there. It's the 52,000. But then we were thinking that, so what would happen if you change the electronic characteristic of the material, but to introduce some kind of conducting material, right? So what we have done is, in the same mesoporous crystalline sulfur-doped C₃N₆, and we added tungsten sulfide nanostructures to improve the conductivity of the material. So to our surprise, and the performance increased from 50,000 to almost 80,000, so 20% more improvement in the performance of this the material. So, and very recently, we could achieve the solar to hydrogen conversion efficiency of almost 4. So our target is to do 5 to meet the target of $2 per kg. So it's like a $3 Australian dollar per kg. So we are almost close. So why I am so fascinated about this research is that it is not only about that performance. So I think, so few Nobel laureates visited my center. Professor Bhavan, I think Etodi knows him very well. Professor Bhavanti, who discovered the quantum dot guy, and also Professor Joachim Frank. And both of them said, and they see the performance and the facility, it is a Nobel Prize discovery. So this is going to change the world. And that was the biggest endorsement that we got from the Nobel Prize winners. So hopefully this may change the world and help the society. And then to commercialize it, we have to make sure that you use the low-cost sacrificial agents. So we use the ethanol, then of course it gives almost similar results with the 1% of the platinum, and then we recycle the ethanol whether it is working or not, and then even after 5 hours of radiation and after 7 cycles, and it works very well. And then we reduce the platinum from 3 weight percentage to 1 weight percentage to 0 weight percentage, and it still works, but with a slight reduction in the performance of this material. So, and this is the basic research, and also we translated the basic research into the pilot scale, 1 meter by 1 meter that you see here, and that is attached with the hydrogen storage container. And in the future, we are going to put this 30-meter by 30-meter pilot plant near the beaches. So, now why this, the discovery is quite unique? Because it's like a solar cell. You can set it up in every household and generate hydrogen by taking the water from the sea. And any petrochemical industries, they need a hydrogen to convert that oil into gasoline. And hydrogen, you can get it from the sea. And steel, green steel, you need a hydrogen, right? Instead of other reducing agent, carbon or whatever, then you can use the hydrogen as such. Aluminum smeltering, copper smeltering, I mean, you just name it. So if we can generate the hydrogen from the seawater, and that will make a huge revolution in the world. So this is the first part of my talk. Then another 5 minutes or so, I'm going to demonstrate to you how the same materials can be used as a electrode material for the batteries and supercapacitors. So to make the electrode material, so we integrated the carbon nitride precursors with the metal organic framework. So I think after this meeting, I'm going to talk to Ettore and his team that because they have made hundreds of new MOF, I mean, we can make use of this one and create the new family of material, right? And one system is here. So we use the diethoxamide and combine with the iron mill 100. Right? And then this iron reacts with the sulfur from diethoxamide to get this iron sulfide nanostructures, and the diethoxamide gives the carbon nitride. So you have an iron sulfide in the carbon nitride in a single system, right? So interestingly, when we put the iron sulfide into this material, the decomposition temperature is increased quite significantly. That means the thermal stability of the material improved quite significantly. And also the iron makes strong bonding with the nitrogen in the carbon nitride matrix. And we use that one as an electrode for the lithium-ion battery. The specific capacity that we got was 1,750 milliampere hour per gram. We compared that one with the other carbon-based material. Our material ranks the top. In the sodium-ion battery, of course, it's a bit low as compared to the other iron sulfide-based system. It's only 300 milliampere hour per gram. So to improve the performance further, what we have done is that we doped transition metal in the metal sulfide. Right? So in this case, we use the manganese sulfide integrated with the diethoxamide and then introduce the iron into the manganese sulfide. So we get the iron substitute to manganese sulfide nanosheets into the carbon nitride material. So interestingly, when they increase the number of the cycles, the performance increases. So this is the nanosheets is converted into small nanoparticle, and that improves the charge transfer. So the performance is almost 2031 milliampere per gram. So how much time I have? It's almost 5 minutes. So I think I'm almost done. Yeah. So the other device into the ultimate clean energy storage conversion device is the carbon capture. So the carbon capture, what we have done is we use the naturally available resources like halloysite nanotubes, which is naturally available. It has got nanoporous structures with a very high surface area. We use them as a template to make a different carbon-based material. And also, we use the waste biomass and integrate it with a two-step salt-assisted strategy to make the carbon nitride with a surface area in the range of 4,000 to 4,500 meters square per gram. So we use this two-step activation technique, the solid-state activation technique. First, we heat the material at 600 degree or 500 degrees centigrade and mix, without adding any salt, and then at 600 or 700 degrees centigrade, and remove the salt with the hot water, and you will get very high surface area carbon. And this is a single step activator. This is normally people use. The surface area is quite less. The amount of CO2 absorption capacity is as almost 16 millimole, which is very low. When we use this two-step activation using the alligator weed, you see here, you have the completely microporous material when you use the less amount of the activation. But when you increase the activation, you get both microporosity and mesoporosity with a very high surface area and large pore volume. And what we got in the CO2 absorption is the 30.4 millimole of CO2 in 30 bar and 6.4 millimole in 1 bar, right? And then when you dope that carbon material, the high surface carbon material with that nitrogen, and how we do that? And we use the casein, which has got a lot of nitrogen, and then integrated with the two-step activation, you get material with a very high surface area of both microporosity and the mesoporosity. And what we found in the CO2 absorption is that almost 2 tons of CO2 per ton of the material, which is much better than the other porous carbon-based material, right? And we use the different biomass precursors like almond skin, casein, alligator weed, grape mark, and lotus. And the almond skin and casein gives much better performance. It's almost 2 tons of CO2 per ton of the adsorbent. And very recently, we used the beetroot as a biomass. Surprisingly, it gives almost 2.25 tons per ton of the material at 30 bar and then 273 K. And that is mainly due to the fact that it has got a hierarchically ordered porous structures with both micro, meso, and the macro pores, and with a very, very high surface area. And as a result, the CO2 absorption capacity of the material is very, very high. And we also converted that adsorbed CO2 into value-added product. This is a photocatalytic CO2 conversion using C₃N₅, and got almost 160, but the performance is not that much high, but it's scientifically it is important. And we use the naturally available catalyst to convert that adsorbed CO2 into value-added product. Use almost 90% conversion and 100% selectivity to methane. This is the nickel and copper based catalyst with a highly ordered porous structures. So, and not only the basic research, but also we translate that basic research into real commercial product. So in our center, we made a bulk production facility for the nanoporous carbon nitride material or carbon material, and we made hundreds of kilograms of the material, and we engaged now the partnership with the Indian company to produce 40 tons of the CO2 per month, right? Sorry, 40 tons of the materials per month, right? And also we made carbon capture plant, that's a 2-ton capacity, and from the 1 gram scale to almost a 2-ton scale. And this was designed and developed by us, and with oxygen, moisture, and pressure sensors. And it can be operated up to 30 bar and the temperature up to 600 degree centigrade. And this is the first example, academic examples of the carbon capture unit using the carbon based material, and this will be commercialized in collaboration with the Indian companies. So I have demonstrated you various technologies like seawater splitting and fuel cell, CO2 capture and conversion, and energy storage. That's a battery. So if you integrate everything with the help of the, integrate everything with the high performance with the help of the advanced nanostructures, and you will be able to design this ultimate clean energy storage and conversion device that will give the continuous supply of energy without using any fossil fuel. So you can drive a car without gasoline, but what you need is sunlight and water and our beautiful material. So of course, it is still in the beginning stage, but I think we are working with the industry partner to commercialize this technology as quickly as possible, right? I'd also like to thank my collaborators and my members. The carbon materials is done by Gurvinder Singh here, and hydrogen research is mainly conducted by Fawaz and Yingyong Kim, and battery research is done by Jangmi Lee and Wangshu Cha, right? Yeah, I think they are the one who are doing the research. I am the guy who is coming here and showing off, right? And finally, thank you so much for your kind attention. Thank you so much.
Thank you, Vinu, for the very informative presentation. And now the discussion is open. I really would like to hear from the students. Yep.
Thank you, Professor, for a wonderful talk. I have a very simple question. For your champion material, for what is the reason for this highest activity for the crystalline mesoporous carbon nitride? Is it the crystallinity or your addition of metal salts?
There are many factors. I think that's a very good question. So there are many factors. The first one is the crystalline, the carbon nitride. So that has got a small defects there, right? And the defects help us to capture the alkali metal ion. And those alkali metal ions suppress that electron hole recombination, right? It's quite significantly, right? And as a result, you are getting a good performance. But if you increase the specific surface, for example, the bulk carbon nitride, and it was like just 20,000. But the mesoporous carbonated, it was 50,000, or tungsten sulfide, and it is 80,000 or something. And that one is increase of the number of the active sites in this material. So it's a combination of all the factors, right? So it's a visible light harvesting and suppression of the electron hole recombination, and then the number of the active sites. So the combination of everything helps you to, and then also the heteroatom, the sulfur. So the combination of everything will just help you. So what we are doing now, because our target is solar to hydrogen conversion efficiency of 5 to 10. Now we achieved only 4, right? And we are integrating with some semiconducting metal organic framework, or even the heterojunctions with the carbon nitride, C₃N₄, C₃N₆, crystalline, and C₃N₆ and doped C₃N₆, the crystalline framework, the heterojunction or the triple heterojunctions to improve the performance of this material. Yeah.
Okay.
Thank you very much for your talk. I have one question regarding the evolution of hydrogen. How about its purity? Is there any other gases being produced or something? Can you have some comment on that?
Yeah, that's again good question. So in this case, we use the sacrificial reagents. So I mean, whatever the hydrogen, the oxygen is produced, I think it can be taken away. But the hydrogen produced is the highly pure. We are not getting any chlorine gas or other gas there, right? And we also did the overall water splitting without any sacrificial agents. The performance is a bit less, but in that case, we get both hydrogen and oxygen. Surprisingly, we were not getting the chlorine. I don't know. And we were also, amused.
Thank you very much.
Okay, any other more comments from the students? I have one general comment on the carbon nitride for the photocatalytic reactions. So you showed the hydrogen production starts from maybe 100 of micromole per gram to maybe tens of micromole per gram. Think this is enough for, say, for commercialization, or we need to get more than that?
No, that's what it is. The commercial calculation they have done is that to make it more commercially viable, then you had to have a solar to hydrogen conversion efficiency of 5 to 10. So now we reached 4, right? But if you reach 5 with the government subsidy, even with the 4, with this government subsidy, yes, it is possible. But once you reach that 5, then we can have the target of $2 per kg. So that's the target that we are going to achieve.
And the enhancement in the production, when you change the ratio between carbon and nitrogen, is because you're changing the band gap, or also you change the conductivity or the mobility of the carbon nitride?
The combination of many factors. See, when I showed you, it's not only the the crystalline carbonated. So I think sulfur doped C₃N₆ in the crystalline carbonated. But when you put this crystalline C₃N₄, the performance is not that high. So the C₃N₆ with the sulfur with the crystallinity, the performance is high. So that clearly tells that it is not only the band gap, but also the chemical composition, the charge transfer, suppression of the electron hole recombination, and so on. So there are a lot of factors that need to be controlled, and if we can fine tune it, even we can improve the performance even further.
Yeah.
So it is just few years of our research. I think there is a lot of room for the improvement and collaboration. So if we do that, then we will be able to achieve what we wanted to in the future.
Thank you. We have time for 1 or 2 more comments.
Yes, Kobayashi.
Right. So before you mentioned ethanol as the sacrificial agent, were you using methanol? I'm curious. And why does the hydrogen production increase when you add sodium chloride? Is the chloride being oxidized also?
Sorry, what was this?
So why does the activity for hydrogen increase when you add sodium chloride?
Yes, so that's what I said. So that's a very good question. See, when the water has the alkali metal content, I mean, when we don't have the alkali metal, and the performance is very, very low. But when you add the alkali metal, so the material has small defects, the crystalline carbon nitrate, because when you heat it up, and some of the carbon decomposed, or the nitrogen, because the thermodynamic stability of the nitrogen in the carbon matrix is very, very low. The nitrogen prefers to stay as the nitrogen molecule rather than making a bonding with the carbon. So at a high temperature, there is a possibility that the nitrogen decomposes and creates a small micro defects. And that defects where the alkali metal ions go and sits. And when it sits there, that significantly suppresses the electron-hole recombination. And that suppression of the electron-hole recombination, we assume that it is helping to get the better performance. But it is not happening when we have the when we use this normal water.
Is this based on like transient absorption studies to look at the recombination?
And also the theoretical study. So I didn't show you the theoretical calculation. Yeah.
And does the chloride get oxidized?
Sorry?
Does the chloride get oxidized?
Yeah, that's what I said, that we couldn't find any chlorine gas or anything in that. Maybe that stays as an ion or something. That was our million-dollar question, says what is happening to the chlorine gas? But the chlorine gas is not coming off.
But you have a sacrificial agent, of course. Maybe that's why.
Yeah. Okay, well, now we are trying to replace that sacrificial agent with the inorganic, the inorganic metal sulfides or whatever. Yeah.
Okay, we have time for one more comment. Yes.
Thank you so much for the interesting talk. My question is mainly about the commercialization of the hydrogen production through the photocatalysis, because mainly for most like industrial sectors, photocatalysis is more costly in terms of separating or regenerating the catalyst from the reaction medium, and then also storing the hydrogen. So how you are overcoming all these challenges in your center, which made the photocatalysis is ready to be commercialized?
Yeah, that's a very, very important question. See, we thought about this one. So when you are producing only hydrogen, and it will be a huge issue, storing the hydrogen and everything. But if you can, that's why I said, integration of this technology is very, very important. So you produce hydrogen and use the hydrogen for the fuel cell and generate energy and use that energy and then store the energy in the batteries and supercapacitors. So you can have a continuous cycle of energy. So thereby, you can avoid the storage or the transportation of something. So that's one. The second thing is storage or the transportation, right? So the technology is already there in the petrochemical industry. See, we never had any big accidents with the hydrogen, because currently the hydrogen is produced from the natural the fossil fuels and then crude oil and so on. And they have their own mechanisms. So it's just a matter of taking that existing technology for storing and then transporting, if you really wanted to use that. But I would strongly recommend to integrate hydrogen production with the hydrogen utilization in one station, so that you don't have to worry about the storage.
Thank you so much for the answer.
Yes.
Okay, thank you again, and we should thank the speaker one more time. Thank you.